your inference of a particular target variable, for example, the label class and so on. So does not tell you how to separate information in that sense. And the question that arises here is, first, well, is entropy and mutual information measure quantities that basically characterize the fundaments of machine learning problems? This is not clear. There are some cases for which you can see that these measures appears naturally, but in general, it's not the case. And are particular instance of these problems for which these information measures can play a key role. For example, to allow you to discover important representations of valuable or meaningful representations of the data. Okay. Now, as I was saying before, the problems are relatively different because in communication, you are dealing with discrete representations of the data, and in learning, you're dealing with continuous representations of the data. Continuous representations of the data may have infinite entropy. Discrete representations of the data don't, but if you're dealing with continuous representations, of course, things can be much different. Now you cannot easily use bits anymore. Another nice intersection between both are the notion of encoders and decoders, but encoders and decoders operate in a single letter per letter basis in learning. So you treat image per image. You don't treat the sequences of image. And in communication, we treat blocks. So that is also a major difference that does not allow you to use universal source coding, for example. And in most of the results in theory, in information theory, are based on known statistics, where in learning, of course, the statistics are unknown. And in learning, you're looking at worst case performance, which are more relative to basically complexity measures on combinatorial problems than specific information measures. All right. But even that, and still there is an important connection between the fields, because learning is very much related to the notion of data compression. When you map sequences of training sets to a specific selection for a predictor on a discrete class according to a VC dimension or any type of metric entropy of covering that you do on the space, this is a compression process. And indeed, this appears in an implicit way in a lot of well-known results in learning, like the PEX, Bayes, or the VC dimension notions relating to the relative to the generalization properties of the learning process. There are concepts like the minimal description length principles that there was in use in statistics to deal with model selection, even though they're not performing well for deep nets until now. And there are more recent concepts like variational encoders, information bottleneck methods that are actively in use to learn better objectives for representation learning. But still we have these more fundamental questions of how to best define representations according to information principles and how to measure the amount of useful information in those representations, useful for the learning task. So I'm going to briefly mention a series of recent work that has been doing in collaboration with students and different collaborators across France and Canada and Austria and US. And I will start with a very basic problem, is that if we would like to use information measures to derive new objectives for learning, of course, we need to be able to estimate those information measures, because information measure depends on the underlying distribution of the data. Yeah? And you don't have that underlying distribution. So to this end, most of the literature on learning continuous information measure was basically using these neighbors estimators. So these nearest neighbors estimators taking a maximization over the points that are the closest one, and this is something that appears to not be differentiable. So they're not easy to implement for to compute the stochastic gradient, and then to use them for specific losses. So more recently, people start working on variational bounds on mutual information. These are essentially lower bounds on mutual information, from which you can differentiate and then optimize your networks. But is it possible in general to estimate information measures? So that was the first question that we asked ourselves. And in order to do that, we basically go back to a very basic problem. We look at the estimation of the continuous differential entropy, which is one of the components of the mutual information. And the differential entropy on real vectors of dimension k, and is given by this expression here. So you see there is an expectation over the unknown distribution, but then you have a low linear function of the distribution itself. Now, the most basic question that we ask is it possible that given some training samples according to a unknown distribution in some class of distribution, is it possible to come up with an estimator, a function of those samples, for which the deviation from the estimated value and the true entropy, it's low with high probability, or the other way around, the deviation larger than epsilon happens with a very low probability. And the answer was negative. It's not possible in general. And for any class P of convex distributions with perhaps unbounding entropies, either infinity or minus infinity, it's not possible to come up with those estimators. So here we basically set up this in the form of a proposition. So they tell you that if your class of a non-distribution is convex, which is very normal assumption, and your distribution, and there are maybe distributions for which the entropy and absolute value is infinity, then it happens that no matter how many samples you have and no matter which estimator you have, it is always possible to come up with one distribution in that class for which the probability of being close from to the true entropy using your estimator is very small. Yeah. And then we start looking at what are sufficient conditions to be able to estimate this, and it happens that sufficient conditions are the Lipschitz conditions on the density in these classes, and they have to be finite support as well. And so under those conditions, it's possible to derive a concentration bound that depends on the important quantities, that's the number of beans that you're using, the dimension of the data, the number of samples, and the Lipschitz constant in that class. So this is using just a histogram counting kernel, but it's possible we have results for general kernels as well. I'm just keeping this. We can discuss afterwards if you are interested in it. Now, this brings us to a practical way of estimating this. So basically, we were looking at variational bounds or variational estimators of the differential entropy. So this is given in the form of uppers and lower bounds to the differential entropy that depends on a variational distribution. So a class of models that you can use to make these bounds tight. Okay, so if you want to have an upper bound, you minimize over this variational distribution. If you want to have a low one, you minimize over these variational distributions, and you will use samples to compute the expectations. And this term here is known as the Renyi divergence, which depends on some parameter alpha, becomes a meta parameter that you can use to tune your estimator. And the way of learning this Renyi divergence is approximating the ratios, the density ratio function using a binary classifier. So I can discuss more about this later. But basically, it happens to be working well. So this is a very toy example of a conditional entropy for Gaussian these variables, in which we plot the entropy as a function of the correlation. And here we plot essentially the gradient of the entropy with respect to the correlation coefficient. And again, you see that in both cases, the approximation and the true value are extremely close for different values of alpha. And we did also explore an application of this with real data for which we don't know the true entropy, but in an interactive manner, we can test if this is helping in some sense. So the typical application for this will be the GANs, generative adversarial networks, in which you would like to train a model to mimic or to learn at some point the distribution of the data. And this is done by using a loss that uses a binary discriminator that try to make the difference between fake and true samples. And the goal of the model is to fault this discriminator. But the problem of GANs in general is that they're not able to capture all modes of the distribution. So in general, they just stuck in a few number of modes. So a way of pushing the GAN to learn modes was maximizing the differential entropy of the generated samples, because differential entropy is a way of maximizing the randomness in that process, and this could be helpful to create or to learn more modes in the distribution. There was a previous work that they were dealing with similar ideas by using mutual information, which is not the same at all. And it happens that this is helping a lot. So here is a fake, this is your fake, it's a fake distribution, but it's your target distribution from which you sample data. This is what a standard GAN is able to learn without any type of regularization. This is what a standard GAN plus the mutual information term is doing, not with the entropy estimator that I'm showing you here. And this is what exactly the GAN plus our entropy estimator is able to learn from the true sample. There are many different models of this. We also look at that what's happening with when you use real images, for example, MNIST images with superimpose multiple digits, 4 digits, to create distributions that have 10,000 modes, because each digit can take 10 values. And then we count in our generator how many different modes the generator is able to capture. We compare to the previous works on that. And it happens that it's not able to learn the 10,000, but it's not far from that. Well, other methods are almost half of the quantity that you would like to learn there. Okay, so I'm just going quickly over this, but it was just a toy application example. Now, a more interesting applications of learning differential entropies and mutual informations arises in the notions of disentangling information in the representation. So how to disentangle different factors or that are labels for you that explain your data. So in particular, we look at this problem for which the tool that we have is well adapted. So suppose that you have features axis. These are your images, any type of continuous data. You have a concept Y that is a label that you would like to preserve in the representation. So you would like to preserve information about your concept Y in your representation. It's your target task. So you don't want to lose that information. And there is another label that is correlated to this, correlated to the features that you would like to remove from your representations. So you would like the representations to be as independent as possible from that label. Okay, this we call this private label, but it's an attribute that you would like to disentangle in the representation. Okay, so you assume you have sample for these features and 2 labels, and you have a general model that is your encoder that is building these representations in such a way that U is going to be as independent as possible of Z and as dependent as possible of Y. All right. So how you can do that? Well, you can basically, when you talk about dependencies, mutual information appears because this is a natural way of measuring the high orders dependencies. It's not only correlation. So if mutual information is 0, the variables are independent for sure. Now, what you could do is that you can maximize mutual information between representations and the target label, and minimize mutual information between the representations and the private label. But to maximize mutual information, you don't need a tool, because the cross-entropy is doing that very well. Okay, so here we're going to essentially minimize this loss. Since I have a minus, I'm maximizing this mutual information, and the cross entropy is doing this very well. To minimize mutual information, things are a bit more different and difficult, because the cross entropy doesn't work well because it's an unbounded measure. So then the mutual information estimator based on the entropy that I mentioned plays an important role, especially because give you an upper bound, and so you want to minimize. So this is what we do here, and the question is whether this works and whether this works on different type of data. So then I'm going to quickly show you different applications of this. So we start with working on these with images, so synthetic and real images. So there are two data sets here in my example. So the one on the left is these are digits, but these are digits from different writers. So the type of digits is exactly the number that you intended to preserve in your presentations, and the writer index is the sensitive attribute that you would like to remove from your presentation. Okay. On the other hand, you have the images of the different people, these synthetic images, and so the emotions of these images are the emotions that you would like to preserve, and the identities of the images is the information that you would like to remove. Okay, so here you see that these are very different tasks, because disentangle emotions from IDs of people is more complicated than disentangle styles of digits from the digits itself. So it's sorry, too quickly. Yes. All right, I have some delay. All right, so here is the what we obtain. So we plot here on the this is for the digit database. We plot the accuracy of a learner that try to learn the regular task information from the representations, and here is the accuracy on the right of a learner that wants to do the same, but on the sensitive levels. As a function of lambda, when lambda exists, you enforce your disentanglement variables. Yeah? So it happens that on the regular task, you don't lose much, because here is a curve, and you go from 97 to 95. On the other hand, on the private task, you go from 25% to almost random guessing. So this line is random guessing. So basically, the disentangle is working very well, and Lambda is able to disentangle this variable. On the other database with the images of the faces, things are a bit more complicated. And of course, you have to pay more from one to the other. This is normal because of the complexity of the task. We have also looked at the completely different application. This is privacy preserving data release on smart meters. So here, this is a real-time application. So here we're using, there's a time series and there's correlation between the samples. So we're dealing with recurrent nets in these models. And why we're interested in this problem? Well, because the information that smart meters release from your houses carries sensitive information, like the type of appliance that you're using, like whether you are home or not on particular periods of the days. Like even in some cases, don't ask me why, but you can even guess the TV channels that you're watching. So this is quite surprising. And so a possible application for these and this that we look at that is in collaboration with Hydro-Quebec in Canada, was using these tools to create representations that are independent of these sensitive features that we may have in these cases. So we just took here a realistic database on which we're interested in hiding the presence of people at home, average of this information over the day. And here you see the accuracy of the attacker, how the attacker succeeds as a function of the distortion of the representations, because of course you don't want to destroy your data, you want to preserve the information of your data with respect to the original samples that you are supposed to communicate. Okay, and so you see that the scales are very different in this course depending on the amount of samples that you give to the attacker. If the attacker has full access to the same samples, has access to partial, all the data sets and so on, of course the curves are very much different. But until the processing is able to preserve the peaks, and so these are the difference between the, on red you have the release data, on blue you have the original data, and the peaks are preserved. Okay. Another application with a completely different data set, and here we're looking at disentangle in a textual representation. So you see that these are a completely different type of data. And in particular, we're looking at two different tasks. One is the fair classification task, in which we perhaps have a target task that is the sentimental analysis, like, for example, positive or negative advices on a particular product, or the mention if a tweet is or not conversational tweets. And your protected attribute here are the race. This is a typical application for fairness, for example. Another case that we're looking at is a condition sentence generation and product transfer. This type of tools are very much in use. And again, the gender here is sensitive information. And you may have multiple label classes here with more than 2 categories, until 5 in this data set that we're using. Okay, I'm not going to go much in details on this because this requires a lot of time to explain how we measure performance. And NLP is nicely than showing pictures. There are no pictures, so I need to start showing sentences, which of course will require a lot of time. But typically you can see that again, the accuracy on the disentangled label that you would like to remove as a function of lambda is getting worse for the attacker. And these are for different alpha parameters in our estimator, compared to what you can achieve using adversarial learning, which is quite flat and you cannot handle the trade-off. It seems that this is really working, and it's working in completely different type of data. Now let me move to something slightly different. It's a bit more technical. That is related to the role of information measures in generalizations, in capabilities of learning algorithms, and the role of information measures in transfer learning in particular. So the first problem that we're looking at is how information measures are related to the representation and to the generalization capabilities of representation learning models. So in particular, if I give you one representation model, this is stochastic encoder that maps data to latent representations, and I have another one, so which one is expected to produce representations that generalize better on data? Okay, and how information measures can be related to that. Of course, there was some heuristic and previous works that showing that there was a connection, but there was not a formal proof of this connection. Right? So in particular, we'll focus on supervised learning, on cross-entropy losses, not general case, but it's very popular. It was basically is done for most of classification problems in these days. And this work provides a formal proof that the mutual information between inputs and features is indeed an upper bound of the generalization error. So this is a uniform deviation between the empirical risk and the risk, and indeed this can be upper bounded as a big O of the square root of the mutual information between the input of your network and the representation, the last output of the last layer of your network. Okay, and this is scaling with this rate according to the number of training samples. Now, this quantity here depends on the data distribution and depends on the specific representation model that you're using. Okay, but this justifies formally why minimizing the empirical risk plus mutual information between inputs and representations is good to improve generalization, because this is directly connected to the generalization capabilities. Indeed, there are some plots that we can show. And in practice, people was not doing this. People was working on an upper bound on this based on the k-elder versions and some prior distribution on the space of the latent variables. Okay, but this is very much related to variational autoencoders, information bottlenecks, and many other models. A second work, and it's the most recent one that appears this year in NIPS, so in 1 month, is related to a very active field, which is the field of few-shot learning. So few-shot learning consists in situations in which you have trained a very complex model, it's a fix, but data have shifted to a new domain, or have shifted in time because the nature is changing of the data, and you have a few samples of that data, like a few shot per class of samples, 1, 2, 3, or 5 examples per class, and you may have more data of this new domain, but it's just given to you without labels. Okay, so how you can readapt or transfer your knowledge to retrain your models on this new data? Only changing the last part of your classifier, so the last layer, the weights of your classifier, not the representations itself. And here, people for this is using meta learning schemes, which are very complex structures that you need to put in place. And we show that mutual information here is improving in between 2 and 5% of the state of the art on all possible combinations of models, which a much simple algorithm without using any type of meta learning tool. Yeah. So what we do is essentially you minimize cross entropy on the few shots of samples with labels that you have, and we maximize the mutual information between the unlabeled data that you have from this domain and the soft predictions of your classifier. So we only optimize the parameters of the last layer, your classifier. Okay, and this is working very well. I'm not going to show you in details this big table of results, but basically these are results on ImageNet, two different sets of ImageNet and the Cube data sets. And clearly the two variations of the method that we're proposing here is outperforming all the others in the state of the art. So mutual information seems to be useful to transfer knowledge from one domain to another domain. Another application of this is in segmentation of images. There is a real images. So segmentation, it's a very important field in medical images and also in self-driving cars. As you can see in these images, you may have information for one domain. So you have images and the information about the segmentation of this given domain, but you don't have much information about the second domain. You only have images and you don't have the segmentation information. So the state of the art here was due to adversarial learning and this AdaptSegNet algorithm. And in particular, we were focusing on MRI images on which this adaptation between domains arises very natural, since you may have differences between the cameras, the machines, and the medical protocols on the different different hospitals. Okay, so what we're using here is you have samples with labels from your source domain. You only have samples from the target domain. You have alignments that you can build yourself from these features of source and target domains. And then you set up a loss that is intended to minimize the information loss between domains. Okay, this turns out to be some type of Kullback level divergence. And it happens that this is working very well. So you see the scores here. This is DICE, is something related to the quality of the segmentation. You see how much this is improving on the state of the art. And in addition to that, something which I think is even more important is much more stable during training. So this is the accuracies as a function of the training steps. And you see this, the blue is our method, and this was the state of the art, which is oscillating a lot. All right, with this, I would like to conclude. So basically, I would say we have good and bad news. The good news is that there are a lot of common things between information theory and deep learning. Common things like encoders, decoders, notions, representations that are very useful in both domains. We're using a lot of information measures as an objectives for learning, like cross entropy, mutual information, or principles like the info gain principle. Differential entropy is a measure of randomness that is very much useful. And it's nice because it's invariant under rotation and translations, but unfortunately it's not under rescalings. So there could be better measures here than the differential entropy. But there is a long way to go. This is also good news in some sense, because this implies that there is a lot of research to be done. But in particular, there may be better measures that are more adapted to learning problems, measures that perhaps introduces geometry of the problem itself, that are not entropies and mutual information. And in particular, this a deep analysis of the theory could help to define a better way of learning representations. Maybe there is a way of clearly showing what a good representation should be according to information principles. So I would say that two messages to take home. The first one is that in these days, in most of work in the machine learning community or AI in general, we focus on performance. As I show you, there's a big tables, always, the new algorithm improve on the previous one and so on. But performance don't tell you the whole thing. Of course, it's just part of the story. And another important part of the story is understanding how predictions are made. How an algorithm may be more trustable, more stable than another one. Perhaps your algorithm is great for one data set, but it doesn't perform well when you have a small shift of the data to another data set. And another one that was less the state of the art is doing much better in that sense. So there are other metrics that can be used to measure performance. In terms of theory, I think there are 4 different concepts that are relatively well known here. Conceptually, but we don't have a theory that mixes them in an adequate manner. The concept of data as a source of empirical evidence, information, which is the unpredictable part of the data, is a noisy part. This is what information is, and so it's not useful for learning. And the redundancy, which is the part of the data that is predictable, the structure of the data, is the one that brings the information to the learner. And knowledge, which is, of course, the concepts of nature that you would like to learn, right? The labels and whatever you would like to predict, all right? So there is some work in theory to be done on that. I would like to thank to a lot of people that has been working with me on this, students and collaborators. The names are all in the order, so there's a nice matching problem here. And with that, I'll be happy to take questions, and thank you for listening to me.
Thank you very much, Pablo. That was a really, really interesting talk.
Hello, Pablo. Thank you for this very interesting talk. I was specifically interested by the part where you talked about disentangling representations and tasks, and you showed examples from language processing. There is a task in natural language processing which consists in trying to de-identify a text, that is, to remove information about the identity of the person who is mentioned in the text. And it seems to me that this might also be subject to the kind of disentangling that you presented. Do you know that task, and do you have ideas on how this might be done?
No, we haven't worked on that. This is very recent. As you can see, this is a submission on iClear, so it's online if you search on that, but it's still under review. This, as far as I understand what you're saying, this will be very much on the line of this. So I will be very happy to talk offline if you're interested on that. And so to explore this, absolutely. Yeah.
Thank you very much.
I mean, it was a bit fast on this because it's, as you know the field, so you know how technical are the different ways of measuring the quality and so on. So yeah, I didn't have much time, but I think it will be worth it to discuss this in detail. Yeah, thank you.
Thanks, Pablo, for your nice talk. I appreciate it very much.
Thank you.
I'm trying to ask the difficult question, something that you tried to explain very well yourself, just to have your impression about this. In my opinion, what you're trying to do with much effort is trying to reconcile the view of traditional, let me say, information theory on one side and artificial intelligence and deep neural networks on the other. And so the difficult question is, how far are them now? Because from ourselves, like myself, coming from the old guard, we are a little bit annoyed by the prevalence of artificial intelligence without any explanation. We would like very much to find a way to predict and to understand how they perform so well. So how far is this explanation in your opinion?
Let me go back to the to rephrase the question. Your question is to how different these fields are in terms of the the assumptions and how far is these ideas of bringing a tool from one field to the other, or how far we are in understanding why these deep neural networks are working so well?
That's, in my opinion, that's two facets of the same problem.
Yes, yes. I mean, understanding why these neural networks are working so well, I mean, there has been a lot of work on that from different perspectives. The one that I'm interested in those that are using information theoretic principles, because it's my field. I never claim that it's the only way to go for that, for sure. There may be other ways of approaching that problem, but I think it's one interesting way. At least it was very useful for communications, as we know. So why not? This can be certainly useful for the learning. But we are far. We are far, and I think it's even though it sounds like a bad news, no, I think it's a good news. But we are far means that there is a lot of work to be done. We are far from, again, I'm talking about my perspective on, for an information theoretic view. We are far because the fields are basically, concepts are similar, but the approach in the definition of the problems is very different. In particular, this thing that I was saying before, the analysis that we are working on blocks in communications, we are doing analysis by blocks. You take a lot of symbols to do compression, not a single one. You communicate over blocks. You don't communicate your information and sampling-wise. Is a big difference when what you do in learning, in which you cannot trade data by blocks because of complexity reasons. So then you cannot use tools as the one that we use in universal coding for communication on compression. So all this theory basically don't fit there. The other important issue is that you cannot measure the I mean, you can always measure the entropy of a representation, but it's not going to give you valuable information like that because it's continuous. And any continuous random variable can have an infinity amount of bits. So it may not be the exact way of measuring the information, the valuable information in the representations. So there has been a lot of excitations around these ideas of information bottleneck. Maybe you heard about that, maybe you have seen these papers, in particular because they have been some work trying to show from Tisby in Jerusalem University, I know him quite well, showing that the process of learning was intended to naturally do compression of the representations and at the same time to maximize the information between representations and the concept, the labels that you would like to predict. And then it has been shown later on that indeed it wasn't the case. This was an artifice of the type of network that they were using, but on different data with a different type of network, this didn't work anymore. And indeed, there was no theory justifying this. The only thing that I can claim on that is what I was showing before, is that this mutual information are connected to the generalization capabilities of the network, but don't explain directly how the algorithm is learning. So yeah, it's very much open. And using different tools, it's also, that's also, there are explanations, like for example, we know now that the overparameterization is a very nice property, because even though the stochastic gradient, which is the tool, does not give you to the optimal solution because your loss is not convex, and because you have an infinity number of different solutions, there are so many different solutions that perform similarly, that there's always one close to what is optimal for your predictor. So this plays an important role. But then still, the theoretical, has been proved for very simple models with a few amount of layers or linear assumptions. So does not really fit the exact models that we use in the reality. So there is still a lot of work to be done. And the problem of these areas, there's a mix of different areas. You have optimization, you have signal processing, you have information theory, and you have algorithms as well. So you need to bring all that together, and it's highly interdisciplinary in that sense. So I think it fits very well the framework of our Labex here.
Thank you very much, Pablo, again.